Okay, for reasons that aren't really worth going into here, I had to make a fresh set of videos reviewing the practice for the first exam, and so here's the first one, starting with question 1. In question 1, you'll be asked to determine the domain of a function, and it will be a function very similar to this that'll have a radical in the denominator. And so we know that we can't have anything inside this radical that would be negative. As a matter of fact, since it's in the denominator, we can't even have anything, any x values that would make it 0, because that would put a 0 in the denominator, and we can't divide by 0. And so what we do is we take whatever's inside the radical here, it's called the radicand, and we set that greater than 0. Not greater than or equal to, we set it greater than 0. And then here I've added both sides, 5 to both sides, and divided by 3 or multiplied by 1/3, and we see that all x greater than 5/3 is that's our domain. And I've indicated that using set builder notation here, although you are certainly welcome to use interval notation if you'd like. But this reads, the domain of f is defined to be the set of all x such that x is greater than 5/3. So that's the domain of this function. Alright, now in the second question, we're asked to determine the break-even points given a revenue and cost function. Well, we break even when we bring in as much revenue as we are spending in cost, so our profit is 0. To solve this, it's really going to be easiest to create this profit function by subtracting the cost function from the revenue function. And so profit equals revenue minus cost. Revenue is x times 400 minus 2x. I have that right here. Then I've subtracted the cost function, and don't forget, I'm subtracting the entire function, so I've put it in, I've put parentheses around it. I'm subtracting the entire thing. So once I've distributed that negative, that subtraction, I have negative 7200. I'm subtracting 7200, and I'm subtracting 100x. The 100x and the 400x are like terms, and so they combine to give us a positive 300x. Now, in this case, I have written the function out the way these authors do in this text, with in order of descending degree. Normally I would put it the other way. That's the way mathematicians tend to do it. But in any case, what we're going to do, probably the most efficient way to solve a quadratic is if we can factor. And I'll just tell you right now that whatever the coefficient of the x squared term is, factor that thing out. Factor it out, and that will make the remaining factorization much easier. So what would have been left, and I'm sorry I didn't type it out here, but what would have been left had I factored a negative 2 out of this function would be positive x squared minus 150x plus 3600. So you might want to write that down. X squared, positive x squared, minus 150x plus 3600. And then at that point, you need values that multiply together to give you 3600, and add together to give you 150, which is the middle term of the version of the function that I just read off. And as I said in class, you don't want to start with very small numbers here, like 1 and 3600, or 2 and 1800, or even 3 and 1200. You want to go a little larger than that, because they're going to have to add up to 150 in this case, but multiply to 3600. Anyway, that's 30 and 120 in this case. If you multiply all this out and then multiply by -2, you'll see that this is exactly what you get. So this tells us that we have a solution at x equals 30, because if we put a 30 in here, 30 minus 30 is 0. We don't care what the rest of this stuff is. 0 times anything is 0. Same can be said for this factor. 120 minus 120 is 0, and that makes all of this 0. So our solutions are 30 and 120. So whatever we're making and selling, if we make and sell 30 of them, we're going to break even. If we make and sell 120, we're going to break even. Anywhere in between those, and we'll make a profit. Now question 3 asks us to calculate some limits. And the first thing you want to do is reduce this rational function here. And your question on the test will be no more difficult to factor than this is. So this is very easy to factor. We just look for two numbers that multiply together to give me -4, but add together to give me -3. And we put those numbers here, 1 and -4. And when we do that, we see that one of the factors is the same as the denominator, and they cancel out. Now, this is not always going to be the case, but it will be for the question that's on the test. I wrote the question on the test just exactly like this. It's just slightly, different. It's a slightly different trinomial up here. And then once you cancel those out, this is the reduced form of the function, x plus 1. And to determine the limits, excuse me, for each of these, you just substitute this value in. So that the limit as x approaches 0 is just a 0 here, plus 1, which equals 1. And for part B, it's the same function as you had here. Our x is just approaching a different value, and that's 4. And so the limit as x approaches 4 is 4 here. 4 plus 1, and that's 5. And finally, the last one is the limit as x approaches -1. And so once again, it's the same function, so we have the same reduced version of the function here. We substitute -1 here, and -1 plus 1 is 0, and 0 plus 1 is 1. So those are our three limits. Alright, in question 4, we are going to use the formal definition of continuity at a point to determine whether a function is continuous at a particular value of x. In this case, it's another rational function, and we're trying to decide if it's continuous at x equals 1. Well, the formal definition of continuity says that we have to have the following three conditions. 1, the limit at this x has to exist, and the function has to be defined at that x, and those two values have to equal one another. So the value of the function at x equals 1 and the limit as x approaches 1 have to be equal. If we have those conditions, then the function is continuous at x equals 1. So first, what I've done here is I've evaluated the function at 1 by substituting 1 in for x. Wherever I've got an x, I put parentheses, and I put 1 into each of those parentheses. After I simplified all that, I had -2/3. Then I want to determine what the limit as x approaches 1 is. And you can see that I factored this out to see if it could be reduced. It cannot be reduced, so I just go ahead and put a 1 in for each of the x's. And 1 minus 2 is negative 1, 1 plus 1 is 1, negative 1 times 2 is negative 2, and then in the denominator I have 1 plus 2 is 3, so the limit as x approaches 1 is negative 2/3. So, since the value of the function at 1 equals the limit as x approaches 1 of this function, then the function is continuous at x equals 1. Now question 5 asks us to use the formal definition of the derivative to show that the derivative of, in this case, x cubed is equal to 3x squared. So to do that, we use the formal definition of the derivative, limit as h approaches 0, of f of x plus h minus f of x over h. In this case, since f of x is x cubed, then f of x plus h is x plus h cubed, x plus h inside these parentheses cubed. Now we did this in class, and we saw that x plus h squared was a good expansion to remember, to recognize that pattern, and then we just here multiply it times 1 more x plus h, and that gives us this expression here. And then we subtract the function, and the function in this case is just x cubed, and we see that x cubed minus x cubed cancel out additively, and then we see that every term in the numerator has an h as a factor. And so we factor that h out, and so instead of 3hx squared, we have 3x squared. Instead of 3h squared, we have 3h. And then instead of h cubed, we have h squared. And then those h's cancel. And this is very important because that keeps us from having a 0 in the denominator. And this becomes our simplified expression. It's the so what we get after the 3 steps in the first 3 steps in the 4-step process, and then we substitute h in, or 0 in for h here, and those terms vanish, and what's left over is 3x squared, and that's exactly what we were trying to show, is that is the derivative of x cubed.